Okay, so in this video we're going to go over a few problems determining whether a sequence is convergent or divergent, and that is actually the question: determine if the following sequences converge or diverge. If they're convergent, find the limit. Okay, so I will solve this, and I will solve different types of sequences, and you will see how I expect you to solve these sequences on the upcoming tests. Okay, so let's start with a warm-up. Let's start with few easy problems. For example, an is equal to n plus 3 over n squared plus 5n plus 6. Well, this is just a Cal 1 question. Basically, here we are looking, as well as all the questions in this video, what is the limit of an as n goes to infinity, right? If this limit exists, then the sequence converges. Well, the limit of an is equal to the limit, of n plus 3 over n squared plus 5n plus 6. When we talk about sequences, n goes to infinity, so this is limit of n. I factor the highest exponent in the numerator, that's n, so I get 1 plus 3 over n over the highest exponent in the denominator is n squared. In the parentheses I have 1 plus, with what do I have to multiply n squared to get 5n? Well, that's 5 over n, right? Plus, with what do I need to multiply n squared to get 6? That's 6 over n squared. And now send n to infinity. First of all, let's cancel one factor of n here, and I have a constant over something that goes to infinity that shrinks to 0. Same with 5 over n, same with 6 over n squared. So you get 1 plus 0 over 1, which is 1. Okay, this was a very simple Cal question. Oops, sorry. I'm left with one factor of n in the denominator, so sorry about that. Don't do this mistake. So I'm left with the limit as n goes to infinity of 1 over n, and as n goes to infinity, 1 over n is equal to 0. I caught my mistake right away because I was just about to say that you can see this is such an easy example. I don't know if you're going to get on your test, but you can think about this. Well, if I have a polynomial divided by a polynomial, if I'm looking for a limit of a rational function as x goes to infinity, then just compare the order of the polynomials. If the order of the polynomials of the polynomial in the denominator is higher, then right away you can conclude that the limit is 0. Okay. Second problem. An is equal to 1 minus n cubed over 70 minus 4n squared. While here the numerator is going to pull to infinity, so right away I know that this is going to be sorry, this is going to be infinity, right? Everything is going to be determined by the numerator. As n goes to infinity, the numerator is going to pull this ratio to infinity, but be careful about this negative sign, right? So we actually don't know how much this exactly is going to be, so let's go step by step and figure that out. So factor out the highest exponent in the numerator. You have 1 over n cubed minus 1 over n squared, the highest exponent in the denominator, 70 over n squared minus 4. Okay, so here you cancel this and this. Okay, send n to infinity. As n goes to infinity, this ratio goes to 0, and also 1 over n cubed goes to 0 as n goes to infinity, which means that this expression converges to a negative n over negative 4. 1n is left here, times negative 1 is negative n. In the denominator you have 1 times 0 minus 4, that's negative 4, right? And now as n goes to infinity, these two cancel. So yes, this sequence is divergent, but I need the right answer. I need the answer that it diverges to positive infinity, right? If you see everything dependent, this sign here was very important, whether if it was plus or minus, that would have changed quite a lot. Okay, so we will continue with this kind of limits that I mean, for which we just apply techniques from Cal 1, an is equal to square root of 2n over n plus 1. Again, same idea. I have a factor out the highest exponent in the denominator. In the numerator, everything is factored form, so there is nothing to be factored. Over 1 over n, cancel the n. This goes to 0 as n goes to infinity. So this approaches, as n goes to infinity, approaches to square root of 2 over 1, or that's just square root of 2. Okay, or sometimes you have expression like this, right? 1 over square root of n squared minus 1 minus square root of n squared plus 1. Okay, and what's the problem with this question? The problem is that as n goes to infinity, we don't really know what happens with the denominator. And why is that? Because in the denominator I have this undetermined form of infinity minus infinity. So n goes to infinity, n squared goes to infinity, square root of that goes to infinity, and then I have minus the same situation here, infinity minus infinity, right? And in that case, I don't know whether this denominator is going to go to infinity. If it does, then 1 over something that goes to infinity, this limit is 0. If this difference goes to 0, then the ratio is going to go to infinity, or if this difference goes to some constant, then the ratio is going to be 1 over that constant. So how to figure out this difference of infinities? Well, let's just rationalize the denominator. So I will multiply it by n squared minus 1 plus square root of n squared plus n. And in the numerator, I have the same expression, which means that I'm just multiplying my sequence by 1. Okay? So I'm multiplying the denominator by its conjugate in order to use this formula, right? Difference of squares. Minus, b squared. Okay? So here I have the limit. As n goes to infinity, the numerator is square root of n squared minus 1 plus square root of n squared plus n over, and now I have, this is my a minus b, right? So here a is equal to square root of n squared minus 1 and b is equal to square root of n squared plus n. So that's equal to a squared. A squared is going to be n squared minus 1 minus, be careful of the parentheses. Everything will be determined by these parentheses. B squared minus b squared, and b is square root of n squared plus n. So b squared is just the expression without the square root, n squared plus n. Okay, so this is equal to the limit. So far there is nothing that I can do in the numerator. Square root of n squared minus 1 plus square root of n squared plus n. Drop the parentheses, n squared minus 1 minus n squared minus n. Okay. So that means that this expression is equal to the limit square root of n squared minus 1 plus square root of n squared plus n over negative 1 minus n. now, as n goes to infinity, the denominator goes to negative infinity and the numerator goes to positive infinity, and it's infinity over infinity case. Don't even try to use orbitals here, that would be totally pointless, but rather try to use techniques learned in Cal 1. Remember that square root of n squared is absolute value of n, right? But n stands for positive integers only. So in our case, square root of n squared is n. So we continue from here. Factor. So basically here I have square root of n squared minus 1 plus square root of n squared plus n is equal to square root of, I factor the highest exponent under the root, n squared 1 minus 1 over n squared plus square root of n squared 1 plus 1 over n. Okay, and then square root of n squared is n. So 1 minus 1 over n squared plus n square root of 1 plus 1 over n over negative n minus 1. And finally, factor n in the numerator and the denominator. Square root of 1 minus n squared plus square root of 1 plus 1 over n over n, or negative n, 1 plus 1 over n. And now this factor is gone. As n goes to infinity, these ratios are going to 0, and you have square root of 1 minus 0 is square root of 1, so square root of 1 is 1, plus the same situation here, 1 over 1 plus 0 is 1, with negative in front is negative 1, so this is a convergent limit and it converges to negative 2. Okay, so there it is, the whole solution. Okay, so now let's do something that it's typical for this class. So just recall that we are usually finding this this sequence in these problems, the alternating sequence, which is nothing else but for different n is negative 1, 1, not for different n, but as n goes to infinity, this is the sequence negative 1, 1, negative 1, 1, and so on and so on. And then we have many versions of the same sequence. For example, cosine of n pi. So when n is 1, I have cosine of pi, which is negative 1. Cosine of 2 pi is 1. Cosine of 3 pi is negative 1, and so on and so on. Or you have sine of, how much this is going to be, sine of pi over 2 times 2n plus 1, right? I want the, or let's say minus 1. Doesn't really matter how you're going to define it, but I want to start with negative 1, just to show you different version of the same sequence. So the first term I want to be 3 pi over 2, so plus. Okay, so when n is 1, I have 3 pi over 2, sine of 3 pi over 2 is negative 1. Then this generates only odd numbers, right? Starting from 3, so the next one is going to be 5 pi over 2, sine of 5 pi over 2. This is 2 pi, which is 4 pi over 2, right? 2 pi. So 5 pi over 2 is going to be 4 pi over 2 plus 1, and that's 5 pi over 2. So sine of 5 pi over 2 is 1, negative 1, 1, and so on and so on. Okay, so be careful of any of these or some other versions of the same sequence. Okay, so this was maybe problem 3. We start with a simple example, 1 plus negative 1 to the power of n. Okay, so let's write a few elements of this sequence. When n is 1, I get 1 minus 1, then 0. When n is 2, negative 1 squared is negative 1 squared is 1, 1 plus 1 is 2. When n is 3, negative 1 to the power 3 is negative 1 plus 1, 0. When n is 4, negative 1 to the power 4 is 1, 1 plus 1 is 2. And as we can see, this sequence alternate not between negative 1 and 1, but between 0 and 2. And at infinity, it doesn't approach anything, so we conclude that this sequence is divergent. Okay? Now, of course, if you compare these to an is equal to 1 plus negative 1 to the power of n over n, okay, then the situation is completely different. Okay, so this is going to be 0. The first term we set it to 0. The second one is going to be 2 over 2, which is 1. The next one is going to be 0 again. Why? Because the numerator is 0, right? So the first term is 0 over 1 is 0. The second term is 2. We calculated that in the previous example. Over n is 2, so 2 over 2. The third element is 0. 0 over 3 is 0. The fourth element is 2 over 4, 0, 2 over 6, 0, 2 over 8, and so on and so on. So the question is whether this sequence now here converges or diverges. Obviously, it alternates between 0 and 1, then 0 and 1/2, so it alternates between 0 and some positive value, but that positive value, right, that comes after the 0, as n goes to infinity, does it happen something to it, right? And as we're going to see, indeed it happens. So this, we call it subsequence approaches to 0. So the sequence is concerned, both subsequences go to 0, so we will conclude that it goes to 0. But because we didn't learn subsequences, how am I going to solve this? Well, a limit of an, first I can split this. That's limit of 1 over n plus the limit of negative 1 to power n over n as n goes to infinity, right? Well, the first limit is 0. That's simple. As n goes to infinity, I have a constant divided by something that goes to infinity, that's 0. Plus, now how I'm going to solve this one? For this one, I will use the squeeze theorem, okay? So, negative 1 to the power of n, right? It's either negative 1 or 1. Now, n is always positive, so if I divide everywhere by n, right, that inequality will not change. And now a constant divided by something that goes to 0 is 0. The constant divided by something that goes to infinity, sorry, I said 0 here, divided by something that goes to infinity is 0. So this by the squeeze theorem has to be 0. So 0 plus 0, this sequence converges to 0. Do you have to use the squeeze theorem here? Well, no, not necessarily. Why? Because you can just write as negative 1 to power n takes only on the values negative 1 and 1. The sequence, sorry, negative 1 to power n over n will eventually go to 0, not infinity, will go to 0 as n goes to infinity. So you see, in order to show me, in order to solve this sequence, okay, in order for you to get the credits, writing this is going to go to 0 is not going to be enough. Okay, you will lose points. So what do you have to write? You have to write this line, for which I guess you will need 10 seconds. Okay, and I need some kind of the justification of the second limit. The first one, you don't have to write anything. Obviously, we learned in Cal 1 how this goes to 0. But for the second one, I need some kind of justification. If the squeeze theorem is too much, then I need an explanation of a very, very, very simple type like this. Okay, now let's see what we're going to do. Let's find the problems. So we can have what did we learn so far? An is equal to -1 to the power of n over n squared minus 3n plus 2 over n cubed minus n. Okay, so here the limit as n goes to infinity of -1 to power n, okay, times, first I'm going to deal with this guy right here, so that's factor of the highest exponent 1 minus 3 over n plus 2 over n squared over n cubed 1 minus 1 over n squared. Okay, so you cancel this, send n to infinity, and then these three ratios will go to 0, so you end up with the limit of -1 to the power of n times, right, I haven't done anything to this factor, so it's right here, times how much? Times 1 over, so I cancel this, right, times 1 over n, but then we're back here, we just get -1 to power n over n, and that limit is 0. Okay, and then we'll do another one of this. So let's say, I even forgot, problem 6, an is equal to cosine of n pi times square root of n squared plus 4 over 2n. Now here we have to be careful a little bit. Limit of an is equal to the limit of cosine of n pi. As I said, get ready to start recognizing this as the alternating part. Here I have n square root of 1 plus 4 over n squared over 2n. Okay, how did I get this term right here? Well, square root of n squared plus 4 is equal to square root of n squared. I factor the highest exponent, 1 plus 4 over n squared. Square root of n squared, we said when we deal with sequences, and it's always positive, so square root of n squared is n. And now you cancel n and n. 4 over n squared goes to 0, and this limit becomes the limit of cosine of n pi, which is nothing else but the sequence -1, 1, -1, 1, and so on and so on, times 1/2. And this limit does not exist. Why does not exist? Because eventually this sequence will just get on the values -1, 1, -1, 1, -1, 1 times 1/2. That means eventually this sequence will just get on the values +1/2, -1/2, +1/2, -1/2. So give me just an explanation here. This sequence will alternate between -1/2 and 1/2, and hence it is divergent. Okay, now what else did we learn? Here I told you to be careful about the limit 1 plus 1 over n to the power of n, and as n goes to infinity, this goes to the constant t. Or we also proved when we talked about the L'Hopital's rule, this is equal to e to power ab. Okay, so for sequences like this, if an is equal to 1 plus 1 plus 7 over n to the power of n, well, this eventual will, what is here, a is 7 and b is 1, so this will alternate to 7 e to power 7 times 1, which is 7, or 8. Now also get ready to adjust this to play with the sign, so 1 minus 4 over 3n to the power of, I don't know, 2n, okay? This is equal to 1 plus negative 4 over 3 over n to the power of 2n. So now this here is my a, and b is 2. This is going to be equal to e to the power negative 4 over 3 times 2, which is e to the power negative 8 over 3. And of course, you can have situation like, again, the same sequence in some kind of disguise, like 3n plus 1 over 3n minus 1 to the power of n. You should be able to recognize that this is a version of the sequence. Of course, you can apply the L'Hopital's rule here. Why? Because it's undetermined exponent. The numerator, the base goes to 1 and the exponent goes to infinity. So yeah, but you can take ln and then you're gonna get infinity times 0 and so on and so on. But if you apply this rule, this is equal to 3n minus 1. I'm subtracting 1 just to get to the same expression as the denominator. If I subtract 1, I have to add 1 plus this 1 is from the original expression over 3n minus 1 to the power of n. So here I have 3n minus 1 over 3n minus 1 plus 2 over 3n minus 1 to the power of n, which is equal to 1 plus 2 over 3n minus 1 to the power of n. Okay, we've been through all of these cases, right? This is in a way a review. So continuing here, so we got to the point where an is 1 plus 2 over 3n minus 1 to the power of n. Now I want this exponent to be the same expression as the denominator, so first I'm going to multiply and divide n by 3, so that's 3n over 3, right? Which now can be written as the cubed root of 1 plus 2 over 3n minus 1 to power 3n. And now in order to get the exponent here to be the same expression as the denominator, I subtract 1 and I add 1. So now an is the cubed root of 1 plus 2 over 3n minus 1 to the power of 3n minus 1, what we wanted, right? And if you have some expression, I don't know, m plus x to power a plus b, this is m plus x to power a times m plus x to power b, right? And that's what I'm going to do. Let's say this is my a and this is my b, so 1 plus 2 over 3n minus 1 to the power of 1. And this finally approaches as n goes to infinity to where? Well, this is going to go to 0 as n goes to infinity, so this whole thing just approaches to 1, right? So we get a cubed root of what? Of e to the power of 2, right? Because now this whole thing is, I can treat it as m. If I ask you what is 1 plus 2 over m to power m as m goes to infinity, well, by the previous by this rule here that was proved when we did L'Hopital's rule, this would be equal to e to the power of 2, right? Doesn't have to be n or m, those are just dummy variables. So I get e squared, or finally that limit converges to e cubed root of e squared, or that's equal to e to the power of 2 over 3. So this is converging and it goes to e to the power of 2 over 3. Okay, so that's it for now. We'll continue in the second video.